Welcome to the flight test briefing for the Albatross aircraft, given by Sahil Sinha. We will be going over several aspects of the aircraft for both static and dynamic conditions. The first aspect is the weight and balance of the aircraft. Here, we see the aircraft in a static condition being placed on 3 scales on the ground. These measure the magnitude of force applied onto the ground by the 3 main gears of the aircraft. These values can then be resolved into their respective moments, which can be added up and divided by the aircraft's total weight to obtain the location for the center of mass of the aircraft. It must be noted that all distances for the moments and the location of the CG are measured from the leading edge of the mean aerodynamic chord, where a positive value represents a distance further aft from this point. A slight deviation of the calculated CG values can be seen when compared with the values set in the simulation. A range of CGs is also provided to demonstrate the furthest aft position of the center of gravity before the aircraft tips over. In the second case, the aircraft's nose is placed against a force transducer, which measures the amount of force exerted by the aircraft when the engine is throttled up. The speed of the engine was gradually increased in 10% steps, and the corresponding values for the thrust produced were marked. A non-linear relationship can be observed with higher increases in thrust for higher engine speeds. Here, the aircraft is seen suspended in the hangar with air being blown at it at a constant velocity and angle of attack. The velocity vectors are marked in blue and the generated lift vectors are marked in green. The deflection of the control surfaces causes the lift vectors to change. The elevators are first deflected in the negative direction, which causes the aircraft to pitch up, then in the positive direction, which causes the aircraft to pitch down. The ailerons are deflected in the positive direction, which causes the aircraft to roll towards port, then deflected in the negative direction, which causes the aircraft to roll towards starboard. The tail is deflected in the positive direction, which causes the aircraft to yaw towards port, and then deflected in the negative direction, which causes the aircraft to yaw towards starboard. It can be seen that the sign of the change in trim angle of attack is consistent with the sign of the elevator input. The aircraft deflects with the nose down moment as the elevators are deflected in a positive direction, and then it deflects with the nose up moment as the elevators are deflected in a negative direction. These deflections were also made at different velocities, with the first being at the stall velocity of 10.5 meters per second. A slow pitch response is observed at this speed. The velocity was then increased to the cruise velocity of 18.9 meters per second. A fast response that decays quicker is observed. Upon increasing the airspeed to the aircraft's maximum flying speed of 27.7 meters per second, the fastest pitch response is observed, with a smaller short period and higher damping ratios. These pitch responses can be compared side by side, with a slower airspeed on the left and faster airspeed on the right. The pitch responses were also compared for different CG positions. At 0% mean aerodynamic chord, the aircraft can be seen at its most stable state. The short period and pitch change is small. However, as the CGs move to 50% mean aerodynamic chord, the aircraft is extremely unstable and stalls as soon as any elevator input is made. The short period is estimated to be 12.74 radians per second compared to the theoretical value of 13.36 radians per second. The steady roll rate as a function of aileron input is measured. It can be seen that larger aileron deflections result in higher roll rates, as expected. The roll rate also increases with increasing airspeed, which was varied between Vstall and Vmax to demonstrate the claim. The rudder deflections produce a side slip angle of the correct sign. The damping in yaw can be seen to be much lower compared to the damping in pitch. The aircraft changes its pitch angle as the CG is moved in the vertical axis. The CG was varied between minus 0.3 meters and 0.3 meters to demonstrate this effect. The pitch angle can be seen as changing in the graph at the bottom of the screen due to the moment produced by the thrust arm. The lift coefficient is plotted against angles of attack for different flap angles. The highest lift coefficient is found to be nearly 1.3 at an angle of attack of just over 10 degrees, with flaps at 30 degrees. The drag polar can also be seen, plotting lift coefficient against drag coefficient for different flap angles. The pitching moment coefficient is plotted against lift coefficient for different elevator angles and different center of mass positions. The neutral point exists where the graph is most horizontal. This should be found at a COM position between 0.35 and 0.6, most likely around 45% of the mean aerodynamic chord. The nose gear was not movable in the simulator, which made the aircraft not steerable while taxiing. The minimum speed needed to achieve wheels off ground without the flaps deployed was found to be just over 21 meters per second, and with flaps deployed, just over 17 meters per second. This is much higher than the predicted stall airspeed of 10.5 meters per second, nearly double. The elevator setting and throttle input for trimmed flight at a cruise speed of 20 meters per second can be seen on screen. This is very close to the minimum speed at which the aircraft can maintain steady flight of 19 meters per second. The highest speed achieved in flight was 45 meters per second.